Hello everybody, and we start our lecture. So today's topic, what is today's topic? Oh yeah, section 17.1, absolute and conditional convergence of series. So I'll start with definition. Definition. If the series which consists of modulus of the terms of our series converges, then the series, the original series AN, converges absolute. And from this definition, it is not clear if there are series which converge absolutely but do not converge themselves. And to understand that this is impossible, we need Coshi criterion, in fact. So, Theorem 1, Coshi criterion of convergence for series. So the series AN converges if and only if for arbitrary epsilon greater than 0 there exists capital N natural such that for all n greater than this capital N and for all natural P, we have the estimate of the following sum: k from n plus 1 up to n plus p a k less than epsilon. That is Coshi criterion. Proof. So, by definition, convergence of a series is equivalent to the convergence of the sequence of partial sums, the sequence of partial sums as n from 1 up to infinity, where Sn is a partial sum, converges. That is just the definition. So, series converges if and only if the sequence of its partial sums converges. Now, for sequences, we know there was a series of theorems, several, in fact, 3 theorems. There were 3 theorems which say, let's say that the sequence converges if and only if the sequence is a Coshi sequence. We had 3 theorems about connection between convergence and Coshi sequences. What means Coshi sequence then? So Sn is a Coshi sequence. By definition, is nothing else but the following. So for arbitrary epsilon greater than 0, there exists capital N number such that for all n greater this capital N, and for all natural p, we have modulo Sn plus p minus Sn less than epsilon. So let me emphasize once again what is written, just a chain of equivalent assertions, right? So we started series converges, then by definition means the sequence of partial sums converges. Then the sequence of partial sum converges if and only if it is a Coshi sequence. Then I wrote by definition what it means to be a Coshi sequence. So everywhere we have equivalence, right? Now look what is this. Sn plus p minus Sn. What is it? So I take sum of the first n plus p terms, right? And subtract the sum of the first n terms. And what is it? First n terms will be cancelled, right? Because a1 exists in both of them, right? a2 and so on up to an. What remains? The sum for all ak with indices from n plus 1 up to n plus p. And then look, that is precisely what is written here, right? So in fact, you see, the proof consists just in a chain of equivalent assertions, right? The only, you see, by the way, we used 2 definitions, right? 2 definitions. Also, this transformation, and most non-trivial thing is that one, right? Just 3 theorems altogether, they were not so simple. Okay, so proof is completed, and the corollary. Which is important for us because of absolute convergence. So if series converges, if a series converges absolutely, then it is convergent. So it means that the usage of words in the definition is not contradictory. I mean, you see that just by definition we cannot say that, I mean, it could be that there are series which converge absolutely, converge absolutely, but diverge nevertheless. Because of the definition, you cannot exclude it. You see, absolute convergence means convergence of this series. And it says nothing about the series itself. But, nevertheless, that's impossible, as this corollary says. So, if it converges absolutely, then for sure it is convergent. Proof. So, the series converges absolutely by definition, means that the series of modulus converges. Then, by Theorem 1, Coshi Criterion, we can write down that there exists for arbitrary epsilon greater than 0, there exists capital N such that for all n greater this capital N and for all p natural, we have modular sum k from n plus 1 up to n plus p modulo ak less than epsilon. That is what follows from Theorem 1. I just wrote using, so instead of ak, I used modulo ak. Now, look. I preserve same sequence of quantifiers, so all of them I keep, and then let us estimate similar sum k from n plus 1 up to n plus p of ak, but without modulus inside. By the triangle inequality, I can put modulus inside. And if I keep all quantifiers the same, then the conclusion is true, right? And what it means? It means this positive expression, right? Non-negative expression is less than epsilon, right? And what it means? Then, what I underline together with this altogether means this line is fulfilled, right? Completely, same line. Without modulus here, what's important. So, once again, by Theorem 1, we conclude that the series now, just our series, converges. That's important. So, you see that indeed, absolute convergence implies convergence of the series itself. So, it's impossible that the series of modulus converges, but series without modulus is divergent. But converse situation is possible. I mean, this series converges, that diverges. That is possible. So, and that is given in another definition. So, definition: if the series converges but not absolutely, then we say it converges conditionally. Conditionally. So that is about main topics of today's lecture. So now all definitions are given. Okay, so now let me formulate an assertion which is very simple but is very useful in solutions of examples. So, I don't want to use the word theorem, just proposition. Proposition. Suppose that we have a series which is represented as a sum of two series. If both series and Cn converge absolutely, then the series An converges absolutely as well. If one of the series Bn and Cn converges absolutely, but another of them converges conditionally, then the series of An converges conditionally. So, proof is very easy, in fact. Look, we can write, so an equals to bn plus cn. Hence, modulo an is bn plus cn less or equal bn plus cn. So, if both bn and cn converge absolutely, it means both of series of modulus converge, right? The sum of two convergent series converges as well, and by comparison theorem, the series of modulo an converges to of modulo, and then it means the series of an converges. So the first part follows from this estimate. Other part, look, for instance, suppose sum of bn converges, but sum of modulo cn diverges. We know one of them should be convergent, another should be divergent for second part, right? Then what we can write? Then we can write, for instance, Cn equals to an minus bn, and modulo Cn less or equal modulo an plus modulo bn then, by the triangle inequality. And then look, so I want to prove that the series of an converges conditionally, right? What means converges conditionally? Means that the series should be convergent, but series of modulus diverges, right? I want to prove that the series of modulus diverges. By contradiction, suppose it converges. Then look, series of modulus an convergent, modulo bn convergent. Hence, by comparison, series of modulus cn converges as well, right? And that is not true. Contradiction. That's so very simple assertion, but it is very useful. Once you represented a series by a sum of two series, then look at absolute convergence. If you have one is absolutely convergent, another conditionally, then the sum is conditionally convergent. Automatically. Okay. Okay. Remark. Analogous assertion is true, is valid. Analogous assertion for improper integrals. Is valid also. So it means I can replace here series by integrals, sequences by functions, and so if an integral is represented as a sum of two improper integrals, one of them converges absolutely, another conditionally, then the sum converges conditionally, and so on. So I'll not formulate it in details, but it is also, as I said, quite useful. Okay, now we proceed with special tests, and first special test, in fact, is a particular case of another test which will be given a little bit later, but it has very nice proof. That is why it is included usually. So, first of all, what are alternate series? Alternate series. These are the following. Bn, where Bn should be non-negative. So, signs alternate. You see. Signs alternate. Plus, minus, plus, minus, plus, minus. That is called alternate series. And Theorem 2, Leibniz test. If Bn is monotone and limit equals to 0, then the alternate series converges. So, you remember that this limit, I mean, when general term of a series tends to 0, that was necessary condition in general, right? Necessary condition. And it turns out that when we have alternate series and also sequence of modulus is monotone, then this necessary condition turns out to be sufficient as well, right? But with some additional suppositions in various suppositions. Alternate sign and also monotonicity in modulus. These are very important conditions. Proof. Proof is in, I would say, in alternate grouping. We'll group terms of our series in two different ways, and it gives the result. So, consider the sequence, let's say, S to n. So, with even number, right? Partial sums. So, we start from 1 up to n, k plus 1, bk. So we consider partial sums of our series, but not all of them, but partial sums with even indices, right? No, it's okay. Okay. Yeah. Then look, what happens? Let me write in details what is it. So k equals to 1, we start with b1. Then b2 with minus, b3 with plus, b4, so on. So up to the very last b2n minus 1 minus b2n. So we stop on b2n, right? Okay. Then look. So, as I said, the proof practically is in grouping. what means to group? To put parentheses, right? Brackets. Let me do it like that first. So we take in pairs, right? Starting from the very first. Then look, what happens with S2n plus 2? So I consider next partial sum with even index, right? So what is it? It is clear from this grouping that what I add, b2n plus 1 minus b2n plus 2, right? So I add a pair of terms. Now look, if bn are non-negative, bn tends to 0, and bn is monotone, what it means? What kind of monotonicity we have? Decreasing, right? Because if it is non-negative, monotone and tends to 0, then it should be decreasing, right? So bn is decreasing, not non-increasing, is non-increasing. Hence, b2n plus 2 is less or equal than b2n plus 1. Right? So, non-increasing. So it means this term in brackets is non-negative, right? So I added something non-negative. It means the result is greater or equal than S2n, right? So I added something non-negative. So what it means, the sequence S2n and from 1 up to infinity is non-decreasing. Non-decreasing, right? Non-decreasing, monotone. That's one story. So another point is to prove that it is bounded. How to do it? Once again, I look at the definition of S2n. So S2n, b1 minus b2 plus b3 minus b4, b2n minus 1, b2n, right? Now, I'll realize another grouping. So, again, we'll consider pairs, but b1, I'll start with next minus b2 minus b3, I put two minuses, right? So on, minus so on, minus b2n minus 2 minus b2n minus 1 minus b2n. So what happens with it? Non-negative, non-negative, non-negative by supposition, right? All bn are non-negative. So what is about S2n? I take b1 and then subtract many non-negative terms. Then for sure this is less or equal than b1, right? Because I subtract many non-negative terms from b1. And what it means? The sequence S to n is non-decreasing and bounded above. Hence, by Weierstrass. Hence, by monotone convergence theorem, monotone convergence Weierstrass theorem, S to n converges. There is limit, right? There is limit S to n equals to S. Okay. Now what's about S to n plus 1? S to n plus B to n plus 1. Plus? Yeah, plus. Now look. This tends to S as n tends to infinity, right? And B to n plus 1 tends to 0 as n tends to infinity by the supposition. Bn tends to 0. Hence, this tends to the same S as n tends to infinity, right? And there was a simple exercise when we considered sequences. So if we have a sequence and we know that its subsequence with even numbers has a limit S, and subsequence with odd numbers has the same limit S, then we deduce that the limit of the whole sequence is also the same S. And it means that our series converges. Okay, there is a question. Could you please repeat again why Bn is non-increasing? Okay, Bn is monotone, right? So it means there are only two possibilities. Either it is non-increasing or non-decreasing, right? If it is non-decreasing, right? So what it means? Right? And so on. Then we know that limit of Bn equals to supremum of Bn. It was during the proof of Weierstrass monotone convergence theorem. If we have non-decreasing sequence, right, then its limit equals to supremum. Okay, but we know the limit is 0. What means supremum of Bn is 0? All Bn are non-negative. So it means that all of them are zeros, right? So the only possibility when we have a sequence Bn which is non-decreasing and satisfies other conditions, I mean Bn non-negative, and the limit Bn equals to 0 is identically 0. So as I told, Leibniz test is a particular case of another test, and I'll give it now. It is called Dirichlet test, and we had Dirichlet test for improper integrals recently, and that is quite analogous. So there is another question about a formula for summation methods, 1 over 1 minus x. So there is a name, of course, that is called Abel's summation effect, but maybe I'll mention it during the topic about power series, but not now. There is a name, but I didn't want to explain this summation method in details. It was just one example, just to show what is it, summation method. Okay. So, theorem 3, sorry. That is Dirichlet test for series. So we had, okay, for improper integrals, we had one theorem which contained two parts, Dirichlet and Abel. So here I prefer to separate them and to give two different. So Dirichlet test for series. If first the sequence of partial sums an equals to sum ak is bounded, and second, the sequence Bn is monotone and limit equals to 0, then the series an Bn converges. Before the proof, I want to explain why Leibniz test is a particular case of Dirichlet. Look. So for Bn, precisely the same, right? Supposition. Monotone and has a limit 0, right? What's about An? So put An equals to minus 1 to the power n plus 1. Then what are capital An? Partial sums. So we have a sequence 1, minus 1, 1, minus 1, and so on, alternate, right? What are partial sums? 1, 0, 1, 0, 1, 0, and so on. That is obviously bounded, right? So first condition is satisfied automatically, right? So it means Leibniz test follows from Dirichlet test immediately. But we proved firstly Leibniz. Then capital An is bounded. So Dirichlet implies Leibniz. Okay, it was not a proof, just as a remark. Now proof. without loss of generality, suppose Bn is non-decreasing, non-increasing, sorry, non-increasing. Then for sure that is non-negative. Then Bn should be non-negative, right? Otherwise, you know, if a sequence is non-increasing, then its limit equals to infimum, right? And we know the limit is 0, so it means infimum is 0, hence all Bn are non-negative. Okay. Now we plan to use Coshi criterion. So what I want to prove, for arbitrary epsilon there exists capital N natural such that for all n greater than capital N and for all natural p we have modulus sum k from n plus 1 up to n plus p a k b k should be less than epsilon. That is what I want to prove. So I'll put question here. That is I want to prove Coshi criterion. Okay. Of course there are many quantifiers here, but what is most important, somehow we need to estimate this sum. So I'll work with this sum. Okay. Let me write it. Sorry. K from n plus 1 up to n plus p, a k, b k. What I plan to do is to transform somehow this sum in such a way to use properties of capital AN and monotonicity of Bn. But so in any case I need to use those partial sums. Now look, if I denote partial sums like that, right, then for sure AK equals to capital A with number k minus capital A with number k minus 1, right? Because capital AK is the sum of the first k terms, capital AK minus 1 is the sum of the first k minus 1 terms. So one term less, and it means we have this one. Then I represent it in this way. And at that moment, what I plan to do is called Abel transform. Abel transform. So, how it works? Look, let me write, so from now on, that is Abel transform. I don't want to write a separate lemma for Abel transform. Quite often you can find many textbooks where Abel transform is given as a separate assertion. I prefer to do it just during the proof. So look, so we start from k equals to n plus 1. Let me write, so a n plus 1 minus capital AN times b n plus 1 plus a capital AN plus 2 minus capital AN plus 1 times, okay, I will erase Leibniz, times bn plus 2 plus so on plus the very last term, capital A n plus p minus capital A n plus p minus 1 times b n plus p. So, what is the main idea of Abel transform? In fact, it is very simple. It's like for Leibniz, for the proof of Leibniz test. An alternate grouping. So once again, we want to group it in a different way. So look, here we have pairs, right? With common multiplier b. So now I want to transform this sum again in pairs, but with common multiplier capital A. Right? So look how we'll do it. Okay, so I want to group now with one capital A, common capital A, right? So look, I have just one term with capital A n plus p, right? No other term like that. So A n plus p times B n plus p. That is just one term, right? Also, I have one term with capital A n, right? Other indices with capital A are greater. So minus capital A n B n plus 1. All other terms I'll group in a different way, right? So let's start from capital A n plus 1. And you see that it is more convenient for me. Yeah, in fact, just let me start with plus, doesn't matter. So plus capital A n plus 1 as a common multiplier. What is in brackets? B n plus 1 minus B n plus 2, right? Plus so on. So all other terms are organized in a similar way. What is the very last? With capital A n plus p minus 1, right? So capital A n plus p minus 1. In brackets, I know the very last with minus b n plus p. So with plus will be with indices with smaller index n plus p minus 1. Okay? Yeah. Let me rewrite it in that way. A n plus p times b n plus p minus capital A n b n plus 1. And let me write it in such a form. Maybe with minus it will be more convenient to me. You will see why. K starts from n plus 1 up to n plus p minus 1. Capital AK times b with number k plus 1 minus bk. So you see, I put minus here and I changed the order. Why I changed it? Because, look, Bn is non-increasing, no, it was bad idea. Non-increasing, I have Bn non-increasing, so plus is better. Don't need to change, just as it was. Bk minus bk plus 1, yeah. Because bk is non-increasing, right? So every bracket is non-negative. That is important. Now look, remember, so that is just Abel transform. I explained what happens in Abel transform, right? Now look, I want to estimate it somehow. It should be less than epsilon. Okay. Why it can be very small? Think. Look. We know capital A, they are bounded, right? And Bn tend to 0. That's important, right? So, okay. Let me use all those facts. So, epsilon over 4, I think, yeah. Okay, so, An, capital An, is bounded. It means there exists constant C such that for all n we have modulus of capital An less or equal than C. That is boundedness of the sequence of partial sums. Okay, Bn tends to 0 by this supposition, right? Tends to 0. What it means? It means, by definition, for arbitrary epsilon greater than 0, there exists capital N natural such that for all n greater than this capital N, I have modulo Bn is less than, okay, I think I should take here epsilon over 4c. That is more convenient for me. We'll see. I think it's okay. So now look. Quantifiers now are defined. I mean, I took arbitrary epsilon greater than 0 and I choose capital N now. Right? So those quantifiers are determined. Then, for all n greater than capital N and for all p natural, what I do, I estimate now modulo sum of those AK, BK. So by Abel transform, that is less or equal, I put modulus everywhere. Modulo An plus P times Bn plus P plus modulo An times Bn plus 1 plus, now most important thing, sum k from n plus 1 up to n plus p minus 1 modulo ak times brackets. That is very important. So here I heavily use monotonicity because that is non-negative, right? That is why I have here brackets, not modulus. That's very important thing at that moment, that I can keep brackets, not modulus. Now look, Okay, after that I can erase Abel transform. I have used it. So, now, what remains? Look, I continue this estimate, but I would like to emphasize that a little bit later I'll use this inequality once again. So let me put here star, because later I'll use just this inequality. And then, look, so this less or equal, look, every modular of A, capital A with an index, right, I'll estimate by capital C, right? So, C times, here I have estimate epsilon over 4C. Why? Because n plus P is for sure greater than capital A. So, epsilon over 4C plus, once again, C times epsilon over 4C plus sum k from 1 n plus 1 up to n plus P minus 1. Once again, I replace here by capital C. And now look, what is important? Because of those brackets, I put C outside of the sum, right? And then, look. How it is called? Oh, I forget what. So, all terms are cancelled. How it is called? Oh. The word, I forget the word. Okay. Telescoping, right. Yeah, telescoping, yeah. Telescoping sum, yeah. Telescoping sum. Telescoping sum, right? So, what is it? I can write, so here I have just epsilon over 2, right? Plus C times B. Okay, what remains? B with smallest, n plus 1 minus B n plus P. Yeah? Yeah, like that. Okay, then that is less or equal. Okay, in fact, Bn are non-negative, so I can forget about that one. We subtract non-negative term. And what remains? So epsilon over 2 plus C times, once again, epsilon over 4C, that is 3 epsilon over 4 less than epsilon. So it means the claim is proved, and the theorem is proved as well, right? Okay, now a twin of Dirichlet test is Abel test. For series, once again for series. If, first, the series converges, and second, the sequence Bn is monotone, and bounded, then the series ANBN converges. So, okay, now once again, without loss of generality, I'll suppose Bn is still non-increasing, but now I cannot assert this one, right? So proof starts practically in the same way. So once again, without loss of generality, suppose Bn is non-increasing, and we use Coshi criterion. I write down it here. Okay, now once again I plan to use star. So the estimate here I plan to use star. So it means the first line is completely the same. But then we'll proceed in a different way. Because in Dirichlet, what we knew? We knew capital A are bounded, Bn tends to 0, right? Now, capital An are partial sums, right? And we know that the series converges. It means the sequence of capital An converges, right? So, now I'll use the same inequality, star, but with slightly different meaning. Look. Recall how we obtained star. Star was obtained when we replaced small ak, little ak, sorry, by capital AK minus capital AK minus 1, right? Up to now, I didn't choose what are capital A. Now I plan to choose. Okay, how? I'll start with B. So Bn is bounded. What it means? It means there exists a constant C such that for all natural n, I have modulo Bn less or equal than C. That is boundedness, right? Now, the series converges. It means that the sum of partial sum, the sequence of partial sums, k from 1 up to n ak, the sequence has a finite limit. Has a finite limit. And it means in particular that remainders of our series tend to 0. So it means that how to do it faster. Let me see. So there exists capital N, right? There exists capital N natural, such that for all n greater than capital N, and for all natural P, I can estimate sum k from n plus 1 up to n plus p, ak, and it is less than epsilon. So I use Coshi criterion for this. So in fact, yeah, I think I can cancel this step just by theorem 1. And I'll choose here epsilon over 4c again. So by Coshi criterion, theorem 1, for arbitrary epsilon greater than 0, I can find capital N such that for all n and so on, right? So now I'll denote by, so what is capital AN? By definition is sum k from capital N plus 1 up to N AK. So I'll start from the first term which appears here. So look, because of convergence of this series, if I'll start from I'll start from a term with large index, right? So all such sums will be small, according to Coshi criterion, right? And I'll start with, let's say, n plus 1, right? Then again, this is true, right? Of course, not for all k, but if k, for all k which are greater or equal than capital N plus 1, right? Okay, I should put capital A with index capital N to be 0 to include it, right? So that is a modification. After that modification, the transformation with the help of Abel transform is completely the same. Because this was main ingredient, right? This was main ingredient. And then we just group the sum in different ways. So star is still valid. And now look. By Coshi criterion, now those terms are less than epsilon over 4c. Look. So in Dirichlet test, what we did? This was less than epsilon over 4c, and that was less than c, right? And now you see, we change roles of those terms. So look, every term is a product, right? So one term of this product is bounded, other is small. And you see now we change roles. In Dirichlet test, Bn was small, capital N was bounded. Now capital N is small, capital A is small, B is bounded, right? So we change roles, that's it. So that is less than C, and so we can proceed in a similar way, right? So once again, that is less than epsilon over 4C. We take it outside, and then, so we finish the proof in completely similar way, right? Completely similar way. Okay, the only thing, so let me write it. What we have, epsilon over 2 plus epsilon over 4C times B n plus 1 minus B n plus P, right? So at that moment, I know what? That is non-negative, right? Non-negative. And I know each of them is bounded. Nothing else. I cannot assert that is non-negative. That is maybe not true, right? So how I can estimate it? I can estimate it just by, so B n plus 1 minus B n plus P. That is non-negative, hence this is modulus of the difference, less or equal Bn plus 1 plus Bn plus P, so less or equal to C. And if I'll use this estimate, so less than epsilon, right? And Abel's test is proved. Okay, so I think I can stop here because, yeah, I think, yeah. Unfortunately, I am not able to, yeah. In fact, there is another way, very short. We can deduce Abel test from Dirichlet, thus just replacing Bn tilde, Bn minus B naught, where B naught is the limit. That is another way to prove Abel test as a consequence of Dirichlet, but I wanted to show how it works because I like this change of roles. That is maybe long a proof, but I like it also. Okay, that's all for today. Thank you for your attention.